recording. Great. Okay, so today we are going to talk about unsupervised machine learning. This is completely different from what we've done so far, in the sense that so far we have been trying to become very, very good at learning from features what kind of outputs they could lead to. And now we are, if you want, going into a completely different direction. The idea is that so far we have been getting better at predicting outputs. For example, when we did this multivariate linear regression, we were trying to predict the number of writes, assuming some parameters, for example, some temperature, humidity, the time of the day, and so on. And our model of linear regression wasn't fantastic, but it was predicting to some extent the bulk of what will happen. We also went and looked at a benchmark to test your neural networks, which is this MINS data set of handwritten digits. And there is where we use deep neural networks, convolutional neural networks. As we were dealing with images, it was useful to start thinking about these convolutional neural networks. And we could also do some augmentation of data augmentation, which is another very interesting trick in your bag of tricks. Okay, and there you learned about regularization, what kind of things you could do, and what is the impact on your analysis. And yesterday, some of you went into also doing some binary classification in particle physics, where the idea was looking at the kinematics of events produced in the Large Hadron Collider, simulated events. One would like to distinguish or get better at distinguishing events that are signal and events that are background, where the signal in yesterday's example was supersymmetric events, and the background were standard model events of producing two leptons and some missing energy. And you could do this to any kind of problem that you have in particle physics, where you want to learn what kind of features you should expect from the kinematic features of your event. Those tend to be subtle. They are not just one single thing that you could do. That's why multivariate analysis are in place already in particle physics. But now with the deep neural networks and convolutional neural networks, you can do it even better. I just wanted to show you this example. That's another example of searching for new physics in particle physics on my own production. So it's just to say that the things that you did yesterday for Susie, you can do them in many other scenarios. Here, what we were looking for is we were looking for the manifestation of some new particles, in this case is new heavy Higgses, that were influencing the way the normal Higgs, the Higgs within the Large Hadron Collider, interacts with gauge bosons, with the forces of nature. And the idea was to train a neural network looking at the kinematic features of events produced by standard model processes and produced by processes where the presence of this particle was included. And typically in this kind of analysis, like they did in the case of Susie, you will have now a classifier, which again is some kind of probability that the higher the number in your classifier, the more signal type your event is, and the lower the value, the more background type your event is. And here what I'm plotting is a distribution of true background events, those are the blue, and true signal events, these are the pink, and what their output classifier was. This is logarithmic, okay? So they'll take this into account. And essentially what you see is that the neural network, after learning, was able to, given another event, was able to give a label of being a standard model or being new physics to a very good accuracy. This separation power was good. And another thing I wanted to tell you from the discussion yesterday is that we were talking about this ROC curve as the true positives versus false positives. But in particle physics, sometimes you want to just relabel and change the what you put in here, you still want to do true positives. Those, in the context of particles physics, you will call them signal acceptance, but you also want to plot essentially the false positives. That means how often when I have an event that is standard model, so that is not new physics, how often do I misidentify it as a new physics? And now we're writing this is also writing this background rejection. And the idea is that in this ROC curve, depending on how big your expected signal and your expected background is, you might want to be somewhere along this line. Forget about these two lines. This is just two different, if you want, possibilities for this new physics particle, whether it's very heavy or it's not that heavy. But let's say that we are here, we have a particular heavy Higgs, and that produces this ROC curve. Ideally, where I would like to be is in a place where I accept as much signal as possible and I reject as much background as possible. And that's why we were saying that it's good to sit, or in principle, you would like to sit on top of this bend of the ROC curve of yesterday. But sometimes your life is not that easy. You cannot just choose where you want to sit. In fact, you know that in each typical event that you produce in the Large Hadron Collider, you are going to have a lot more probability of having produced a standard model one than a BSM or a new physics one. And then you need to increase and make tighter your criteria for rejecting background. Otherwise, your total signal over background is going to be too small. And so what you will do is to precisely look along this curve to do that. This is just to recap some of the things we have seen in supervised machine learning and the applications that we have done. Now we are going to delve into a completely different set of problems. Here, so far, we knew the labels. We knew that we are going to learn from a data set where we know that inputs lead to outputs. And what the task is of learning is the learning, given a new set of inputs, predict the output very well. So learning very well what some inputs will lead to. Our learning in this case was guided, it was supervised by a reward in which every time you run the neural network and got better at predicting the outputs, you say, that's good, we are going in the right direction. You were trying to get into the high accuracy. You knew the accuracy because you knew the true labels. But now imagine that we didn't know what we were looking for, that we just had data and no outputs, nothing. We just had data of events, if you want, situations where this and that happened. But there is no information and then led to an output. We don't have that. We just know that when we observe stuff out there, there is different situations, and we just don't know whether there are any patterns in those situations that we can learn from. Why, let's say, what would be the reasons why we don't have labels? Why do we don't have this information? It could be because they are just unknown. I just don't know. I'm making observations, and I'm still at the level of not knowing whether there are correlations. Input leads to output. Or it could be that in principle you could obtain those labels, but they are just too costly, which is quite typical when you think in terms of big data. Now we are talking about huge amounts of data, and it might well be that there is no annotator out there, that there is no human saying, oh, that's good. So, for example, in the case of medical diagnosis, it could be that you have hundreds of thousands of X-rays, and nobody has gone and said, this X-ray corresponds to this patient with those characteristics, just because there is no annotators to do that. But still the information is there. And you know that there is something to mine in this information. Or it could be that you have a data set where you know relations between inputs and outputs, but you still believe that there is something else in this data that you haven't already perceived, that you haven't already obtained. So you want to keep mining a data set, although you know that there is already a set of predicted labels. So there are many reasons sorry, why you would like to do some kind of mining or unsupervised learning from your data. Now, this is a snapshot of some of the events and the representation of the events that the supersymmetric data set that I gave you yesterday was, right? This is just each of these rows over here corresponds to a particular event, and the columns are their characteristics. There are some kinematic features. And those events had a final column over here that you cannot see that said whether this event was produced as signal or as background. But imagine we don't have this column. What we are going to have is the normal situation in the Large Hadron Collider. You are going to have events, period, and you don't know where they come from. Just don't know. You just observe events. And you would like to assign labels to it to understand whether among those events are there any that are interesting. But what happens? The first problem, so let's say that this is your problem. What you do as a physicist, you will start thinking on possible physical relations. So you will start looking at some of these events. You will try to understand through your model, in this case the standard model, what kind of behavior you should expect and see whether there is anything unusual there and build some criteria of deviation respect to the standard model, blah, blah. Essentially, you will do your physics thinking. And to start thinking about these physical relations, you will start by plotting things, right? With the idea that we as physicists are good at finding from raw features, like here we just have some measurements, we start combining them into a higher level feature, something more abstract but closer to manifest the real underlying laws of physics. For example, in events in the Hadron Collider, what you have is some directionality information and some deposition of energy in different parts of your detector. Then you take this information of timing, tracks, and so on, and then you transform it into objects, into what you call a jet with some clustering, a lepton, a muon, and so on. And from those objects, what these people have done is then build kinematic features, like, for example, they take a lepton, look at the force momentum, they combine with another lepton, then they deduce the missing energy, they look at angular distributions and so on. So you see in the typical particle physics analysis, you will go from a raw measurement to something a bit more, if you want, more massaged, if you want. That is, for example, the objects that you are identifying, leptons, jets, and so on, to something a bit higher level and more abstract, which is combinations of those objects in terms of things that will appear in our physical equations, like momenta, angular distributions, and so on. So you try to obtain the best data representation, a representation which will manifest a behavior that is expected from your physical intuition. And it might take a long time, of course. It might take you developing a theory that guides the experiment into measuring things and combining them in the right way to actually allow this data to show its real nature behind. And this is, for example, what we were discussing in a previous lecture. We were saying that when we look at this redshift versus distance, you clearly see a linear relation. But you have to think to take all these objects and the measurements you can do with them and decide to plot it in this particular way to actually find that there is this linear relation. So in terms of these two variables, redshift and distance, the relation is clear. in terms of the raw measurements that have been done by these people, the information will not be clear. And the path from raw measurements to actually finding the true manifest nature what's going on, it takes physical understanding, data representation, and mostly for us is to actually find possible physics laws that can lead to these kind of things. Okay, so it requires a lot of human thinking. That's what I mean. And this human thinking is done by representing things, by showing the data in a way that is convenient, and then it shows in its full colors what is going on behind. So now we are in this situation, right? We would like to mine data that could be very raw. It could be that it's not even like in the case of supersymmetry already digested PT, eta, phi, and so on. Could be just what we observe, period, with no other level of handling. And we would like to see on this data, which tends to be higher dimensional, some behavior that by human eye allows us to then do a study. Okay. Here we cannot play the games we were playing, sorry, when we're doing supervising. When we are supervising our algorithms, we can allow ourselves to feed into, for example, deep neural networks or convolutional neural networks, very raw features and completely not manipulated. That's the power of these neural networks and deep learning in general, which is you really don't, if something is there to be learned, you probably will learn it by, again, doing things like regularizing and so on, by adjusting the architecture. But there is something to be learned and little and subtle things to be done. The network will do it because at each layer in the network, what the network is doing is transforming your original, maybe very raw sequence of data into something a bit more abstract, a bit more abstract, a bit more abstract. So that at the end of the whole network, you end up with objects that have nothing to do with the things you have inputted actually. Okay? But when we are talking about unsupervised learning, we cannot rely on this because we just don't have the labels that are telling the network that is doing well. You are doing well. Continue doing this kind of abstraction. That direction is good. Okay. We need to be a bit smarter in the way we do things. Do you have any questions? Because you are very quiet and no, you are here. Okay. If you have any questions, interrupt, please. Feel free to do so. Okay, so the idea, what we are going to do today is to start moving in the direction of mining data sets that have no labels, where there is no guidance that we can give the algorithm in terms of predicting power. We just need to find things, something, a pattern in this data that we didn't know about before. And everything we do will start with data visualization, okay? And the problem is that we can't visualize things in more than 3 dimensions. Humans are quite limited. But most of the data we want to mine is high dimensional. The first thing one needs to do is to use dimensional reduction. The idea is that even though the data is higher dimensional, it could be that some of the features I'm taking into account are actually not that important. And even if they are important, they are so correlated with other features that the whole true dimensionality of my problem could be lower. For example, think on these things over here. This is called the Swiss roll or whatever. Imagine that instead of having this wrapping, imagine that I remove it. Remove the green wrapping and just focus on the data points. And imagine that you are shown these data points with these colors and stuff, and you are asked to find patterns on them. If you didn't know that this came from this kind of wrapping, it will be quite hard. And also, depending on where you look, what orientation you give to your three-dimensional visualization, it can be quite hard. But if you find the good wrapping, if you find that actually this data set is best visualized by wrapping it with this green thing and projecting it into D, then it's clear. Then in that particular and very useful projection of your data, you see that there are actually features that can be seen. But if you have tried any other thing, you will not see this. You will see a mess. Sorry. So the reduction, or dimensional reduction from a number of features to fewer features isn't simply projecting into a lower dimensional space in whatever dimension you want, of one dimension at a time. There is a choice there to be made which will determine whether you learn or you don't learn. And this is the direction to project. You would like to project in directions that keep as much information as possible, as it happens here. For example, look at this other example where I'm going from two-dimensional information to one-dimensional information. If I choose a projection from 2D to 1D, like this, like where I just essentially look it from a direction like here, I'm going to lose all the correlations and all the interesting things that are happening in 2D. My problem here is genuinely 2D, and the representation is 2D. If I try to reduce it to 1D, I'm going to lose the information. Whereas, for example, this same system, if I try to represent it in 3D, like for example, you take this triangle and then put it in a three-dimensional space, I can start rotating it and moving and so on. But clearly, there is a way to reduce from 3 dimensions to 2 dimensions and still keep the information, because this is genuinely 2D. So this dimensional reduction is not just a preset way of doing things. It's something that will depend on your data and the true correlations that exist on your data. Now, we know in physics, we are used to this problem, in particular in statistical dynamics, thermodynamics, and so on. You know that that's what we do all the time. We take highly complex micro features, and then when we are talking about huge amounts of those particles, for example, moving at a certain velocities and so on, we are able to describe all these highly complicated situations in terms of a few macroscopic features: temperature, volume, and so on. Although the system is genuinely quite complex, when I'm looking at it from some distance, actually the dimensional reduction in terms of what features are important is there. You go from huge amount of features, momenta, position, and so on of your particles, to a lower amount of features, temperature, pressure, and so on. Okay, so this can work. If nature or the data is nice enough, what is going to happen is that although our data looks extremely complex, and when we look at it from that standpoint, we don't gain any insight, any power of prediction. When we start looking at more macro or more, let's say, extended behavior, we are able to actually understand what's going on. So here we would like to get something similar, to do something similar with our data. So there are many ways of doing this dimensional reduction that is smart, in the sense that we do go from a high dimensional space to a smaller dimensional space, maintaining most of the information that we would like to get out of them. So the direction to project out dimensions is important. We need a criteria. There are many criteria to do so, but the one that is most commonly used and the one that you would use first is what is called the principal component analysis, or PCA. I'm going to explain PCA to you using this example we've gone through already. So this first notebook you had on the predicting bike rides as a function of the different characteristics of the day, like the time of the day, the season, holiday, working day, weather, and so on. And one thing I did for you in the notebook was to precisely plot correlations. The correlation matrix is precisely just taking your data and then doing this transformation. Then you normalize it, and that's what you get. And this is something that you have some intuition about already. Things that are highly correlated means that they do depend a lot on each other. So if one changes in one direction, the other is going to change in the same direction. Things that are not correlated means that they are independent from each other. They don't care so much about variations in one or the other. And when we did this, we already had a kind of discussion, very rough, about feature engineering, big name for nothing but to realize that in this data set and all these inputs, some of those were redundant. For example, the clearly redundant input is this temperature versus real field, because those are highly correlated unless there is a huge wind, right? If it's hot, and it can go from 30 to 32, 33, given the humidity, or it can go from 0 degrees to minus 10 degrees if there is a lot of wind chill. But, in typical situations, those will be correlated. So there was no point of maintaining temperature and real field. And that's what we did. We dropped this. And we also played with dropping features, keeping others, seeing how our prediction was changing or wasn't changing, and so on. For example, there are other things we can see here. There is a clear correlation between total rentals and register, because most users are already registered. There are clear correlations, so the light colors, between, for example, all the characteristics of weather. For example, our indications about good weather or bad weather is, of course, related to temperature, humidity, wind speed as well. For example, you can also see that there is some anti-correlation. You see this dark color over here? I don't know if you see my pointer. When you see this color over here, you see that it is an anti-correlation. So it's also a correlation, it's just negative. So these two, working day or not and casual, are related. Probably because during working days, most users are registered users, whereas casual users maybe come mostly from holidays, people that are visiting the city, and then they decide to rent a bike. Okay, so this is a good example where we have some intuition. First, that there are many features that are correlated to each other. Some are so redundant that you can directly drop them, like this one. Some are slightly correlated. So it looks like we are keeping all these features, and actually we could just take a good linear combination of some of these features, and maybe that linear combination of temperature, humidity, wind speed, working day, or weather could be good enough. It will maintain most of the information that we need to predict the behavior. So hopefully here you see that there is probably a possibility of doing some linear combination of the initial features to go from number of features, let's say in this case were 10 or something like that, to actually keep only few, let's say 2 or 3 features. This is precisely dimensional reduction. The dimensionality of this problem, the way we set up, is high. But in reality, we see by inspecting the correlation metrics that the dimensionality could be reduced. And one simple and straightforward way of reducing it is to try to find linear combinations of those features that maintain most of the correlations. Okay, so how do we do this in practice? It's nothing too hard. We take the correlation matrix and diagonalize it. X, remember, is a matrix that is non-diagonal, it's not a square, it's rectangular. So the diagonalization is slightly more complicated, but you guys are doing your PhD or higher, so no problem. Essentially, you diagonalize it, and the result of the diagonalization is going to be the matrix containing the order eigenvalues, and this matrix that contains the eigenvectors that correspond to the directions of these eigenvalues. So the idea of PCA is simply look at these eigenvalues. They tend to be ordered. There is probably, as we see over here, there is probably going to be 2 or 3 combinations of features that will be important, and the rest will be redundant. So when we do this diagonalization, we will find that indeed that's the case. We see that the sum of the eigenvalues are large and most of the rest are very small. Okay, so dimensional reduction in this case, doing PCA corresponds to going from the initial space, the original space with, going back, these features, where X made from these features, to change to a new data set where the new X here, let me call it another name, is made of those linear combinations that have the higher values. This new data set will have a smaller number of features. We have dimensionally reduced our problem. Okay. Any questions? No? Okay, so I move on. Okay, PCA is good. It's the first thing you will do. It's a first try of visualization, but there is a limitation. PCA is simple and also numerically not costly at all. It's just a simple finding linear combinations. But if we want to do something a bit more, let's say, sophisticated, we probably want to do the following. Often, what we would like to preserve is some local structures that appear in higher dimensions. Meaning that when you imagine that you can represent the data in the real higher dimensional space, you will see there, if you were able to visualize it, you will see there are clusters of behavior, things that are close to each other, things that have commonalities. But when you do PCA is just doing some linear things, so it doesn't take into account these local structures. So there is another procedure of doing this dimensional reduction, which is called TSNE, which is T-stochastic neighbor embedding, which again is the math behind is pretty long, but essentially, in a nutshell, what it does, TSNE, it takes probabilities, correlations between the data points on the original space. So it goes and computes all this PAJ on the original data space with some sigma. Sigma is a parameter that you are going to vary to. Simply a kind of add more noise to your procedure. And then you make choices of possible latent space, so possible combinations of your initial data points. In this latent space, let's call the new coordinates y. This is not prediction, this is y of a new coordinate space. This is a smaller dimensional space. This is the latent space. And we can compute similar thing. We can compute things like this, correlations among these guys. And having computed these two things, you can provide a criteria for minimization. The idea is that this minimization criteria will try to preserve in the latent space as many correlations as possible that were in the original space. The math of it is complicated in the sense that it's probably something you wouldn't think in 5 minutes. And what kind of minimization criteria that is shown over there is just a minimization criteria that has been shown to perform well. But the initial idea is the same, is try to find a transformation from initial or original space to latent space that presents correlations that are local, that also had to do with the distance. The thing, for example, let me go back here, that here we are talking about correlations in total. We are talking about all the data points and how correlated they are. Here we are actually inspecting point by point in this data set. So it's more a local measure of correlation. And the idea is that you do this, you would use this minimization criteria, and then you find which latent space leads to the minimum for this criteria. The way to do that is, again, it's going to be more computational intensive, it will take longer, but it has lots of advantages because TSNE, and we are going to use this in the notebook, is much, much better at finding true patterns in your data. It's
Sorry,
also,
Veronica, can I ask something?
Sure, sure.
So I'm a bit confused about this TSNA. So you start with your dataset, which is XI, so the X, right? The original.
Mm-hmm.
And then your new, so after you apply this procedure, you will end up with the Ys, right?
Yeah.
And this is the one you will input in your neural network.
Not in a neural network, but it will be, let me clarify this. Both PCA and TSNE are just dimensional reduction criteria, nothing. We are not doing an analysis yet. We are trying to find what reduced space, when we plot it, will give us the best representation of the data. And by the best representation of the data, there are many things you can decide that means best. But in the case of TSNE, is the representation that when you reduce to a smaller space, you still see the same kind of local clustering that you will expect in the higher dimensional space.
So you want the Pij to be equal to the Qij?
Or you want this difference to be exactly.
And what is the transformation between the X and Y?
This is what you are going to be running over precisely. You are going to, you start with your data, this is set, and you are going to try all different possibilities over here.
But when you say all different possibilities, you mean linear combinations? You mean something more complex?
Something more complex, yeah.
So but is there something standard that you would do, or?
Yes, there is a set of transformations that you look for when you do this mapping from X to Y. And if you want to know more, go to this review. Mm-hmm. These equations are taken from there, so that you can see the whole discussion. In fact, in this review, there is not a lot of discussion either about what is done, but precisely in this course, I cannot, spend all the time explaining every single algorithm. The idea is to at least give you some physical understanding of them.
Yes, thanks.
Yeah.
Sorry, Veronica, this is Maria. One more question. What is the sigma I?
Sigma I is very good. Is this a parameter that you put? This is a parameter that you are going to randomize over.
Exactly. Okay, I see. Okay, interesting. Okay.
Which the physical, you already have your physical understanding that this is probably some kind of noise that you are adding to your data to see how robust your procedure is.
Mm-hmm. Okay, thanks. Mm-hmm. Yes.
Now, why using this particular form of QIJ and not another? This is again based on some statistical analysis. The criteria for minimization is one particular choice that has been shown to be, efficient, but there are many others. That's why I also want to fixate on explaining this is what is done precisely in TSNE, because what I would like you to do is to try different versions and see which one is going to work for you. There are tens of ways of doing dimensional reduction. And in your data set, one, for example, just doing PCA might be perfect, and TSNE might be an overkill, or it can even be not a good procedure because your data is not truly local, that it doesn't have these features that you expect from it. Okay, good. So for the moment, all we've done is or what I've done, is to tell you about a couple of possibilities for doing dimensional reduction from high dimensions that we cannot visualize to lower dimensions that we can visualize. And there, as I showed you too, there are like tens of different ways of doing the dimensional reduction with advantages, disadvantages.
One question.
Yeah.
Sorry. Then the only reason because we reduce dimensions is because we want to visualize, because we only can visualize 3 dimensions at most. So I don't know if we always can reduce the dimensions as much.
That's a good question. Yes, in fact, I should clarify. We want to dimensionally reduce to be able to visualize it better, and that's why it's called data visualization techniques and so on. But in reality, as you are pointing out, it's not just that. We actually want to dimensionally reduce because if we now have a representation of the data that is simpler, but it still contains the information that the original data set had, doing the next thing we are going to do, which is clustering algorithms or other ways, criteria for clustering data, is feasible. If you try to do clustering, you try to find patterns in your data in a very high dimensional and highly correlated set of data, this clustering is not going to be effective. So it's not just because we are humans and limited and stupid. No, it's also because our methods that now we are going to apply to try to find patterns will only work if we have done our homework before, which is to reduce the problem to a lower dimensionality, which still maintains most of the info that could be obtained and allows this procedure to be done. Okay, so the next thing is, okay, so I take my data, dimensionally reduce it, I look at it and try to understand physically what's going on and use my intuition. But at the end, you need a criteria to try to find patterns. And this is the concept of clustering. Again, people working in experimental particle physics, they immediately get what it is. The idea is that now that we have reduced dimensionality, we actually projecting on a space that is clear with PCA or TSNE. We can and we see some separation, like is happening here. Then and only then you can start thinking about clustering. There are many ways of finding patterns in data. Clustering is one of them. It's the first one you will do because it's the one that, let's say, is more intuitive. You have a set of data. You would like to think that there are some patterns there that you have not discovered. And the first thing you do is to try to find a visualization of the data that shows that there are indeed clusters of behavior, where you want to actually assign some meaning to the fact that all these data points are in the same cluster. Okay. In fact, this is just the plot I've done for you in the notebook, where, and I'll explain to you in a second, but the colors actually represent the minced numbers. And the clustering done with TSNE, this projection is good. It's really separating most of the numbers well. Now, clustering, as again many of you already know, is an iterative procedure. You start with some parameters like the number of clusters, the cluster size, the criteria to be in or out of the cluster, and you go over it and over it and over it until you reach some other criteria which tells you to stop clustering. And then inside this, there is, like in jet physics, you will have things like trimming and so on. I guess what I want to tell you is it's iterative, it's costly, it's easy to make a mistake, Also, you could end up merging things that are genuinely not, they are actually from different phenomena. For example, you could merge jets that come from different patterns, and that's not what you want to do. So it's something that you have to be smart at. And little changes here or there can give you an edge, especially if you are dealing with very complicated situations, like in the LSC, you will be dealing with a loss of underlying event and jets that are, of large R and so on. So the mathematical expressions of how to do clustering, since it's this iterative procedure, are cumbersome, many definitions of running parameters and so on. So I decided not to put them here. If you really want to look at them and try to understand them in detail, just go ahead, please. And in this, this reference I gave you here, let me just show you again. This paper is very well explained. Okay, but at least the meaning of clustering, the intuitive meaning, is clear. You see that these points are close to each other and separated from the others. So you intuitively would like to give this to the meaning of a cluster. Here the situation is more messy, but you can still see some level of separation between those and so on. Now, there are many ways of doing this clustering. The same way that in jet physics, there are many clustering methods, anti-KT and so on. And then on top of them, there are many ways of dealing with merging, trimming, and so on. Here is the same. There are many ways of defining clustering and try to, once you have projected into a space that is tractable, you might want to apply different clustering methods. And what this is shown here, this is from Scikit, the web page of Scikit. This is showing different data sets. Think on these data sets at the beginning as they are all in black and they are given to you, human. And then I ask you, in this data set, how many clusters do you see? And you, human, will immediately say, I see two. I see a circle outside and a circle inside. In this one, how many clusters you see? Well, I see this cluster and this cluster. For you, it's clear, no? If I gave you all this in black, for you, it would be a bit difficult to see the density of points. And you might not be able to realize that actually there could be a cluster here, and another cluster here, but it also depends on the density of how many points I get. If I gave you this one, you will say there are probably 3 clusters, this one, this one, this one. 3 clusters, clearly. And here, again, you as a human would not be able to tell me because it looks like a square. And yeah, you see that there are some types of maybe more density on the edges, but it's not clear. Okay. With this discussion, I just want to point out that you as a human, there are things that you will find super easy that, for example, this clustering method is not able to do. For example, here is clustering this and it's clustering this, which to you as a human doesn't make sense. Or here, right? Or here is also doing something that you will not do if you are asked to do clustering. Whereas this one is doing okay and this one is doing something, but you don't know why. And then this is the mini-batch k-means, affinity propagation, mean shift, spectral clustering, world, blah, blah, blah. There are many, 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 many of them. What you can see is that depending on the data set, for example, for this first data set, these guys are doing great, whereas the others, or this one as well, whereas the others do not. For this second data set, again, the same suspects are doing well, but the others do not. For this data set, we also have, let's say, good behavior in this case, or in this case, but not in the others. You see that not the same algorithm is working in the sense of achieving what you will do as a human when it comes to a different data set. When it comes to these blobs, everybody is doing well. So clearly all this clustering is working when it comes to very clearly separated blobs of data. But when it comes to this continuous data and the possible correlations that there are inside, each algorithm is doing whatever, and in particular, these algorithms over here, which found clusters correctly on these places, or at least this one, doesn't find any kind of clustering here. With all this discussion, I don't want to kind of scare you and tell, like you get the impression that this is whatever and you could get whatever. No, the information I want to pass on is that a priori, you have no clear understanding of which clustering method is going to be best suited to your data set. Once you dimensionally reduce it, it might well be that by studying all these algorithms, you realize that maybe these algorithms of clustering are better at separating things of this type, right? That are close, but it looks more for continuous behavior, like is happening here. Whereas precisely when things are not separated but are continuous, it's not able to give you any information. You can also see that, for example, k-means, which is the one I'm going to use today for you, is doing well in well-separated blobs, but in most of the other tasks, it's not doing that well. So it's not the greatest clustering method ever, but it's one that is just has a criteria of distance and is pretty simple to use. So what we are going to do today, we are going to follow actually a suggestion made by one of the students. Somebody was asking the other day, well, if we had this means data set, just the images, and we didn't have the labels, would our algorithm realize that there are clusters of behavior, that there are 7s and there are 8s and there are 2s and there are 1s and so on? And if so, to what accuracy? Let's say if we were able to separate the images into numbers of a different type, what accuracy would this unsupervised learning method would achieve? Now, this can be done. This is what I'm doing for you in this notebook. And what you are going to find is that, and this is typical, the unsupervised learning has less predictive power than supervised learning. Unless you are really not doing your job correctly, if you train on a data set that is supervised, and you then try to mine something on the same data set in an unsupervised way, you should do better with supervision because you are supervising well. You are telling actually the true reward of, yes, this prediction was correct, or no, this prediction was not correct. So nevertheless, using this dimensional reduction of TSNE and k-means, in that data set, we are going to achieve an accuracy of 94%. So these clustering methods, although even when you apply them to images, like is the case of the means data set, and images that have variability, because if you remember those handwritten symbols, a 2, a 5, a 9, and so on, they could look quite similar because people have so much variability in their handwriting. But still, with these simple clustering methods, we are going to get 94% accuracy. And this is in a task where we have not tell, the only thing we are going to do, and this is something we are going to do, is to tell the algorithm to search for 10 clusters. The notebook today is very short. I also felt a bit bad because I feel that you guys are working super hard on the notebooks. The one of CNN is particularly difficult, and it's not something you can do certainly in 2 hours. So today I wanted to give you something shorter, so at least you get everything you need from this lesson by just running and understanding this notebook. I want you to realize that all these visualization and clustering methods are available like this with a simple line of code. So it's not like you have to be deciding, oh, I'm going to now code TSNE, and now I'm going to do affinity clustering method and it takes a long time. No, it's you just call this subroutine and it does it for you. I want you to go over it to try to understand the things that are shown there, the representation, 2D, 3D, and so on. And if you have more time and let's say the energy, I have given to you a homework task. I'd like you to do the same, data mining and supervised learning with your own choice of data set. That maybe what you're working on, you have already some data, given it maybe as a comma separated numbers, an Excel, or it could be that you have images. And you could use today's notebook to actually start visualizing and doing dimensional reduction on your particular data set. And if you don't have any and you will still like to do this task, I'm giving you a suggestion, a link to a particular challenge. So Samsung gave a data challenge to people, gave information on the gyroscope data from their phones, from Galaxy and S3, from users. They also gave the label to this data, meaning that sometimes the users with their phone, they were going upstairs, going downstairs, they were running, they were lying down, and I like you to, if you don't have your own choice of data set, go over this one. I give you also a solution. Not me, somebody has done a solution, a very simple and not very good solution on how to do this data mining. But I like you to precisely use what I've shown you in this notebook and apply it to this solution to get a better understanding of the commonalities of behavior of these users. Okay? Do you have any questions?
Sorry, Veronica, can you hear me?
Yes, I hear you.
I have a question. I've been looking to the link of the Kaggle exercise that you gave us,
Yes.
and in that one there are two links, and one of them say download the data from here, but the link that he put doesn't work. So I'm not sure which one are the data that we should use.
Yeah, use the other link.
Okay, so
It just brings you to our UCI repository and then you can download everything.
so I can use the other one. Okay.
Yes, the first link.
Okay, thanks.
And again, these unsupervised methods are, I just wanted, like you do the notebook today and you're done. I would say this is for you the day. But if you want to continue learning, I think on other possibilities. There are so many things where we do have data and have no clue of whether there are any patterns. And now you have some tools, you will have some tools to actually start mining it. Okay? So we reconvened in 1 hour and a half. You don't have more questions? Yeah, I forgot to tell you. So on Monday, we are going to talk about reinforcement learning. We learned about supervised learning, unsupervised learning, and another category of learning is called reinforcement. And it's a very cool idea as well. So that's what we will do on Monday. Okay? So